Hello, Math Study students. In this lesson, we're going to take a look at our 8.5 through 8.7 notes, and we're going to be talking about probability. So let's start with the definition of probability. Probability is a branch of mathematics that analyzes random experiments. That is to say, experiments where one cannot predict the outcome. Maybe another way to say that is that you don't know the outcome until the experiment has happened. Like you don't know the outcome of a game until the two teams play the game. So that's what probability is. So let's take a look at probability in terms of a Venn diagram. We're going to let our universal set represent all equally likely possible outcomes of a random experiment. And we're going to let A represent a particular event or a particular outcome. So to find the probability of that particular outcome of A happening, we're going to take a ratio of the number of ways that A can occur and the number of items in the universal set. Now, there are three consequences of this law. First of all, the probability of the universal set happening would be the number of items in U to the number of items in U. Of course, that would be equal to 1. So in other words, the probability of a certain event is always going to be 1, all right? The probability of nothing happening. So an impossible event, you can think of it that way. An impossible event happening will be the number of ways that can happen out of the number of possibilities in the universal set. So that would be the probability of an impossible event, and the probability of an impossible event is 0, okay? But most probabilities are going to fall somewhere between 0 and 1, all right? So most probabilities, if the event is not impossible or the event is not certain, then the probability will always be some ratio that falls between 0 and 1. So let's look at a couple examples. Let's start with the example of tossing an unbiased coin. So just like at the beginning of the Super Bowl, they'll flip a coin, and it's unbiased. Either heads or tails can come up. So our universal set would represent all possible outcomes, so we can either get heads or we can get tails, okay? The probability of heads happening will be the number of ways that we can get heads out of the number of possible outcomes in the universal set. Well, there's only one way to get heads, and there are two possible outcomes, so that probability is one half. The probability of tails would be the number of ways that we can get tails, the ratio of the number of ways that we can get tails to the number of possible outcomes. So again, there's only one tail out of two possible outcomes, so the probability of getting tails is 1/2. How about the example of rolling an unbiased dice? Of course, that's a cube. It has 6 sides, so let's just assume it's a normal dice that you're used to seeing. So that means our possible outcomes in the universal set would be 1, 2, 3, 4, 5, and 6, okay? Now, the probability of any one of those happening, the probability of rolling a 1 or the probability of rolling a 2 or 3 or 4 or 5 or the probability of rolling a 6, well, there's only one of each of those numbers and there's 6 possible outcomes, so that probability would be of rolling any of those numbers would be 1 out of 6. So let's continue talking about rolling an unbiased dice, and let's look at this. Let event A be rolling an even number and event B rolling a prime number. So for those two events, we're going to use a Venn diagram to help us with our thinking. So A would be even numbers, and B is prime numbers. So this set represents the even numbers that could come up on a dice. This would be the prime numbers, okay? Now, there is one number that would be in the intersection of those two sets, and that's the number 2, because the number 2 is both prime and even. The other possible prime, and then the other possible even outcomes would be 4 and 6, okay? The other prime numbers that can occur would be 3 and 5, so that leaves one number we haven't accounted for yet, and that's the number 1. Well, by definition, a prime number, obviously 1 is not even, so it wouldn't be in circle A. It's also not in circle B, because by definition, a prime number is a number that's bigger than 1. So we're going to place 1 right here. Okay, so now let's look at our probabilities. The probability of rolling an even number. Well, if you look at the even number circle, there's 3 possible outcomes. So if we look at the ratio of the number of ways that A can occur to the number of possibilities in the universal set, That would be there are 3 even numbers out of 6 possible outcomes, and then that reduces to 1/2. Okay? The probability of B, rolling a prime number. Well, again, it's going to be the same probability because we have 1, 2, 3 ways that that can happen. So the number of ways that B can happen, there's 6 possibilities out of the number of possibilities in our universal set. Turns out to be 3 out of 6, which also reduces to 1/2. Okay? And then how about this one? The probability of rolling a number less than 3. Well, how many numbers are there less than 3? That is just 1 and 2. So there's only, the number of ways that C can happen out of the number of possibilities in the universal set would be 2 out of 6, which reduces to 1/3. Okay. The next one is the probability of rolling an even prime number. Well, there's one of those. There's one even prime number. So there's one way that can happen out of 6. So I'm going to skip writing this count ratio. I'm going to go ahead and jump to our ratio. There's one possibility of that happening out of 6. So that probability is 1/6. Okay, the next one is the probability of rolling an odd prime number. Okay, well, there are 2 odd prime numbers out of 6. So that probability, that would be 2 out of 6. And then the last one, the probability of, or let F be the event of rolling a prime or an even number. So that would be the probability of A or B happening, okay? So the union of those 2 sets would be all 2, 4, 4 and 6, obviously, and 2, because that's in set A, and then 3, 5, and 2 also. Now we don't need to count 2 twice, so that's 1, 2, 3, 4, 5 ways that you could be either, that the number that comes up on the dice could either be even or prime. So there's 5 ways that can happen out of 6, so our probability is 5 out of 6. So now let's talk about this idea of complementary events. The way we represent that is we call A prime the complementary event. So the probability of that complementary event happening would be 1 minus the probability of A prime. Okay, so 1 is the probability of it happening with 100% certainty. So if we subtract the probability of A prime happening, then we have oh, I'm sorry, I need to write that, I need to fix that. It would be the probability of just A, not A prime. There we go. So the probability of A prime happening would be the probability of 100%, something happening 100% minus the probability of A happening. And we call that the probability of A prime. So let's look at this example. A jar contains 7 green marbles, 3 red marbles, and 4 blue marbles. Let event A be drawing a red marble out of the jar. So that event, let's just jot this down over to the side, drawing a red marble out of the jar, probability of A happening. Well, how many red marbles are there? There are 3 marbles out of, what would the universal set contain? We have 7 green, 3 red, and 4 blue, so that's a total of 14. Okay, so the probability of A happening would be 3 out of 14. So that means the probability of the complement of A happening would be 1 minus the probability of A happening. The probability, oops, I forgot my 14 over here. The probability of A happening, which is 3 out of 14. So that's going to be, let me just go ahead and quick get a like denominator. 14 out of 14 minus 3 out of 14 would be 11 out of 14. So that's the probability of drawing the complement, or drawing a number that's not, a marble that's not red. Now let's look at some examples of combined events. So the probability of A union B. Okay, so the probability of the union of A and B, okay, to figure that out, we will find the probability of A plus the probability of B, but as we'll see in a second in our example, whoops, that should be minus, we're going to have to subtract the probability of both of those things happening at the same time, so we don't count events twice. That would be the probability of A intersect B, okay? So let's take a look at an example. Let A be the event of drawing a red card from the deck of cards, okay? So this is, I guess I should have called this A instead of red, but our event A would be drawing a red card, and then event B would be drawing a king from a standard deck of cards. So this represents the kings. okay? So I want to draw, see if I can squeeze this in here. What cards would be both red and be a king? So we've got the king of hearts, and then also we've got the king of diamonds. I don't know how well you can see that. And then that leaves the other kings would be the king of clubs. I'm not going to be able to draw this very well. And the king of spades. There we go. Okay, so to find the probability of being a red king. Okay, so another way to think of that is, think of it as the probability of the union of A and B, okay? So to be a red king, that means we need to take the probability of A happening plus the probability of B happening, and then we need to subtract the probability of both things happening at the same time. So what is the probability of A? Remember, A was drawing a red card. So if you recall, half of the deck, by the way, there are 52 cards in the deck, half of the deck is red, so the probability of being a red card would be 26 out of 52, okay? The probability of B, that would be a king, that would be 4 over 52. But then if we stop there, our probability will not be correct because we will have counted these two cards twice. So we need to subtract the probability of being both red and a king at the same time. We can see there are two of those. So we need to subtract 2 out of 52. Okay, so simplifying then, we get that is equal to 28 out of 52. You can leave your answer like that, or if you prefer, you can reduce it and call it 7 out of 13. Both of these would be considered correct. Now we're going to talk about conditional probability. So what is conditional probability? Well, conditional probability is the probability that A has occurred given that B has already occurred, and we write it like this. It will look like this. The probability of A, then put a vertical bar, and then put B. So sometimes we would read this as the probability of A given that B has already occurred, okay? So there's a formula you need to learn for that. The probability of A given B, we find it by doing this. We'll take the probability of both A and B happening at the same time to the probability of B happening. Okay, so let's take a look at an example where we can use this formula. Okay, in this example we have in a class of 29 students, 20 study French, 15 students study Italian, and 8 study both. A student is chosen randomly from the class. Find the probability that the student, well, let's first of all find the probability that student studies French. Well, to help us with that, let's go ahead and build our Venn diagram from this information. Okay, so let's start with the fact that there's 8 students that study both French and Italian. So let's put 8 in the intersection. Now, if there are 20 students that study French, this French circle, okay, remember 8 of those have already been counted, so, and if there's 20 total, that means that there are 12 students that study French only, okay? If there are 15 students that study Italian, when you look at the Italian circle, we've already counted the 8 that study both, so that means there are 7 left that study Italian only. And then that totals, let's see, 27, so that's 27 out of the 29 students total. So that means in our universal set, there are 2 students that study neither language, okay? So now we can find these probabilities. Let's start with the probability that a student studies French. Well, if you look at the French circle, there are a total of 20 students in the French circle out of the 29 students in the class. So the probability that a student studies French would be 20 out of 29, okay? The probability that a student studies neither language, that's these 2 guys right here. There's 2 of them out of 29 in the class, so that probability is 2 out of 29, okay? Letter C, studies at least 1 language. Okay, so that means at least 1 means 1 or 2. So we wouldn't count these 2 guys because they don't study at least 1 language, but these guys do. They study at least 1 language. These guys study at least 1 language. In fact, they study 2, and these guys study at least 1 language. So if we total that, we get 27. So the probability that a student in this class studies at least one language would be 27 out of 29. Okay, now let's take a look at letter D. What's the probability that a student studies Italian given that he or she studies French? So we're going to look at this two different ways. Let's do the theory first. So that would be the probability that the student studies Italian, studies, hold on, let me fix that, studies Italian, put a vertical bar, given that they study French. Okay, so using this formula up here, then what we would calculate is we would take the probability that they study Italian and French at the same time over the probability that they study French. Okay, so looking at our Venn diagram, how many study Italian and French at the same time? That would be 8 of them. So 8 out of how many study just French? Look at the French circle, that would be out of 20. So we get 8 out of 20, or if you want to reduce that, that would reduce all the way down to 2/5. Either answer is fine. Okay, so here we worked it out with the theory, but you don't always have to write this out. The Venn diagram will show you that. The probability that they study Italian, given that they study French, well, you're only going to consider these 20 students that study French, and then given they study French, how many study Italian? That would be the 8 out of that 20. How about this one? Studies French, given that he or she studies Italian. So there are 15 people that study Italian, so how many study French, given that they study Italian? That would be 8 out of our universal set of 15. So the probability of French, given, I forgot my vertical bar, given that they study Italian, that's the probability that they study both French and Italian out of the probability of Italian. So what you'll see when you do these conditional probabilities is that conditional probabilities reduces your universal set from the whole set down to, in this case, just 15. So it's 8 out of 15. So now let's look at two special cases. One will be mutually exclusive events, and the other one will be mathematically independent events. Two different things. Okay, mutually exclusive, I think you'll have a sense for this. Mutually exclusive events means A and B are mutually exclusive if whenever A occurs, it is impossible for B to occur, and similarly, when B occurs, it is impossible for A to occur. So, a good example of that would be flipping a coin. That's why they flip a coin at the beginning of the Super Bowl, because there's only one possibility that can come out. You're going to get heads or tails. If heads comes up, it's impossible to have tails. If tails comes up, it's impossible to have heads. So the way to look at this theoretically would be to say events A and B are mutually exclusive if and only if the probability of both things happening at the same time is 0. It's impossible for a coin to land on heads and tails at the same time. So let's look at an example. And that example says the numbers 3, 4, 5, 6, 7, 8, 9, 10 are each written on identical cards and placed in a bag. A random experiment is that a card is selected at random from the bag. Let A be the event that a prime number is chosen, and let B be the event that an even number is chosen. So we're going to draw a Venn diagram to show that these events are mutually exclusive. In other words, we're going to show that the probability of a number being both prime and even from this universal set at the same time is 0. Okay? So we'll draw a rectangle to represent our universal set. Okay? Then we have our set A, which represents the, let's see, A was the prime numbers in the bag, and then B is the set that it is even. Okay, so let's start placing all the numbers in one or the other. Remember, A was prime and B is even. So 3 is prime, 5 is prime, 7 is prime. So let's put those in there, 3 and 5 and 7. Any other prime numbers? I think that's it. Okay, so let's pull out, so let's just mark out what we've used, 3, 5, and 7. Then our even numbers are 4, 6, 8, and 10. So 4, 6, 8, and 10. So they're going to go in this circle, 4, 6, 8, and 10. And then don't forget about this number 9. It's in the universal set. It's in the bag, but it's neither prime prime, nor even. So 9 needs to be somewhere over here outside of those circles. Okay, now what we were trying to show, that the probability of A and B happening at the same time, that those two events are mutually exclusive. Well, if you look at our Venn diagram, the intersection is empty, okay? So the probability of A and B happening at the same time is equal to 0. Whoops, equal to 0. So now let's talk about mathematically independent events. So here's the definition. A and B are mathematically independent when the probability that A occurs remains the same given that B has occurred. Okay, let's think of a couple of examples. One example would be that I flip a penny and then I flip a nickel. Okay, so after I flip the penny, which I could get heads or tails on, the next I'm going to flip a nickel. Well, I could get heads or tails on the nickel. It's not in any effect on what I got. What the outcome of flipping the penny has no effect at all on the outcome when I flip the nickel. Another example, I had some friends one time that had 5 boys and they were pregnant with their 6th child, and so everybody said, well, surely this one's going to be a girl. Well, that's not true, because they could have had 100 boys. The probability of having a girl every time that she was pregnant was still 1/2. So that's an example where the probability that A occurs having that girl remains the same given that they've already had 6, 10, or 11 boys, okay? So let's write the theory. Events A and B are independent if and only if the probability of A and B happening at the same time is equal to the probability of A times the probability of B, okay? So let's look at an example. We put the numbers, this has a typo in it. I need you to mark out number 10. That shouldn't be in this list. So take that out, and now let's look at the example. Okay, the numbers 2, 3, 4, 5, 6, 7, 8, and 9 are each written on identical cards and placed in a bag. A random experiment is a card is selected at random from the bag. Let A be the event that an odd number is chosen, and B be the event that a square is chosen. So we're going to draw a Venn diagram and show that these two events are mathematically independent. So we'll start by drawing a rectangle that represents the universal set. So all of these numbers have to be somewhere in our universal set, okay? Then let's draw a circle for event A. Remember, that was event A. Let me just underline. Event A is that we choose an odd. And then event B would be in the event that we choose a square number, okay? So now we need to place every one of these numbers somewhere in the universal set. So the number 2 is neither odd nor a square, so I'm going to put 2 outside of the 2 circles. 3 is odd, but not a square, so it's going to go in circle A. 4 is even. I'm sorry, not even. I meant to say 4 is a perfect square, but it's not odd, so it's going to go inside of B and outside of A. So we have 2, 3, 4 placed, okay? 5 is odd, but not a perfect square, so it goes in A and outside of B. 6 is even, but, 6 is neither odd nor a perfect square, so 6 goes out here. 7 is odd, but not a perfect square, so it's going to go in the A circle. But outside of the circle B. 8 is neither a perfect square nor odd, but it's still in the universal set, so put it inside the rectangle. And then 9 is that one number that's both a perfect square and it's odd, so it's going to go in the intersection of A and B. So now let's show that these two events, that a number being drawn is odd and a number being drawn as a perfect square, are mathematically independent. So we'll do that by showing that the probability of A and B happening at the same time is the same as the probability of A times the probability of B. So let's figure out all those probabilities. Okay, first of all, let's start with the probability of A happening. Well, let me do this. I'm going to leave a little bit of space. The probability of A happening. Well, how many events, how many elements are there in set A? There are 1, 2, 3, 4 in set A. Out of the universal set has 1, 2, 3, 4, 5, 6, 7, 8 numbers. So that would be 4 out of 8. 4 out of 8, okay? What's the probability of B happening, that we draw a perfect square? Well, there are 2 perfect squares in our universal set out of 8, so that would be 2 out of 8. And then the probability of both things happening at the same time, okay, that a number is both odd and a perfect square, well, that would be this one, number 9. So there's one of those out of 9. Not out of 9, out of 8, okay? So now let's go back and put all these numbers into our formula. The probability of A and B happening at the same time was 1 out of 8, okay? Now, is that equal to the probability of A, which is 4 out of 8, times the probability of B, which is 2 out of 8? Well, if you multiply by multiplying the numerators and multiplying the denominators, then on the top we would get 8. 4 times 2 is 8. And on the bottom, 8 times 8 is 64. And if we take 8 out of 64 and reduce it, we're going to get 1 over 8. So we have shown that the probability of both things happening at the same time is equal to the product of the probability of A times the probability of 9. So we have shown that these two events are mathematically independent. Okay, so when I see you again in class, you'll be working some problems over these notes. So if you have any questions, be sure and ask me then.